Hello, grade 12. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabudiwa Sos Ugobela Wemet. And without any further ado, let's just get into the video. So we are given cubic function secrets, and as the title says, it's cubic function secrets. So I'm going to tell you things that they don't want you to know, but then that will probably make your life easier when approaching cubic function questions in your grade 12. So please watch until the end so that you get the most out of this video here. Right, so now we can see that the white graph here, that's your f of x, is representing the cubic function. So let's start by that. We have our white graph there, which is f of x is representing, so f of x, that's your cubic function. And then we have our f prime x, that's your parabola function, right? But the parabola function in this is what we call the derivative function, right? Because as you can see there, it's indicated as f prime x. So it is the derivative function. And then we have f second prime x. This is the straight line graph or the linear graph, but then it is representing the second derivative function. So this is the second derivative function. Now, why have I drawn a cubic function along with the parabola and the straight line? It's because now the parabola and the straight line will be telling us about the behavior of the cubic function at certain points and certain values, right? So number one, we know that this point here is known as the local maximum of the cubic function, and this point here is known as the local minimum. So these are your stationary points. Now we have three stationary points. The other point is found here, which is known as the point of inflection, right? So point of inflection. Now we'll be looking at the behavior of the cubic function, but then now we want to relate that behavior to the parabola function, which is the first derivative, and also the straight line function, which is the second derivative function, right? So this is the relationship that you'll have to note when it comes to those questions, because most of the time they can give you the parabola function and they want you to comment on what will be happening on the cubic function. Now, if you don't know the relationship between these functions, it becomes a challenge to answer those type of questions. So now let's go about it, and then let's discover something that will be very, very beneficial into you having to solve your questions there. So, okay. Then to first look at the function of the first derivative. So let's write it in yellow so that you understand that I'm talking about the derivative function. So to understand what f prime x is actually telling us, which is the gradient function, So as it suggests, it is the gradient function. That means it is telling you, it is reporting about the gradient. It is reporting about the gradient of the cubic function. This is reporting to us about the gradient of the cubic function. So it's telling us that what is the gradient of the cubic function at certain points. So if I wanted to find the gradient of the cubic function, I would just simply look at the yellow graph. I would just simply look at the parabola graph. And then at that certain point, then it will be able to report back to me what is the gradient. So let's say, for example, I wanted to find the gradient at this point here, right? Then all I had to do is draw a straight line like this. And then when it hits that point, then I go to my y-axis. Let's pretend that our y-axis is here, right? So let me just draw a straight line over here to represent my y-axis like that. Then if I wanted to know about the gradient of the parabola at that certain point, what I would normally do is just draw a straight line here that will then touch the derivative function, and then I draw a line horizontally that will go and touch my coordinate here, or a point here on the y-axis. Now, if the point it touches on the y-axis, let's assume it's 2, then that means at this certain point here, at this certain x value here, the gradient of the cubic function is 2, right? So I hope that makes sense. Then let's say I'm interested in finding the gradient at the local minimum and the local maximum point. So what do? I simply just draw a straight line from that local minimum, and then draw it up until it hits the parabola function, which is your derivative function. Now, as soon as it hits that, I need to correspond it to the y value that I get. Now, you can see that that value here of the local minimum corresponds to the y-intercept, to the x-intercept of the parabola, the x-intercept, meant to say. Now, let's go for the local minimum point. Again, when we draw a vertical line, we can see that it corresponds to the x-intercept, another x-intercept of the parabola. Now, if we have the x-intercept, if we have this point corresponding to the x-intercept, what does it tell you? We know that for the x-intercept, y is 0. So this is telling you that at the local minimum and the local maximum, the gradient of the cubic function is what? Is 0. So f prime x is 0. Remember, f prime x means the gradient of f of x, the derivative of f of x. So that means the gradient of cubic function at local and at local mean and local max is equals to what? 0. Now, this is why every time you are calculating the points, the local maximum and the local minimum, every time you are calculating the stationary points, what do you do when you are calculating your stationary points? Your teachers have been telling you, when you calculate the stationary point, you need to take your f of x and then derive it. When you derive it, you get what? F prime x. But after getting f prime x, what are you supposed to do with the f prime x? You should equate it to 0. Now you know why you equate it to 0. It's because the gradient of the local minimum and the local maximum point, the local minimum here and the local maximum is 0. Right? So the gradient at those particular point is 0. Hence, you are taking your f prime x and equating it to 0. Right? And then by virtue of doing that, you are actually trying to calculate the, you are actually trying to equate that to that so that you find the x values, right? So the x values that you are going to find are the x-intercepts, right? So your stationary points, the x-coordinate of the stationary points are actually the x-intercepts of the parabola graph. Now, after finding these x values, your -2 and 4, they then tell you, take these values and then substitute them into the original graph. So you substitute them back to what? To f of x. But why are you substituting them in f of x and not in f prime x? Remember, if you substitute them in f prime x, what you're going to get is 0. Because the -2 and 4 here are the x-intercept of the parabola graph. But this graph here is only good to tell us about the gradient, but then it cannot tell us about the y-coordinate. So in order to find the y-coordinate, we must take this same values here and then substitute them back into the original equation of f of x, which is in the form of ax cubed bx squared plus cx plus d, and then to find the y values of the local and minimum, local maximum and local minimum point. Okay, so now that's the first thing that the gradient is telling us about, right? So it helps us to predict, number one, the points of the local minimum and the local maximum. How do we do that? We do it by just directing it straight to the x-intercept of the parabola function. And then after finding the x-coordinate, we go back to the original formula and then we find the y-coordinate, right? Now, to solidify what I just spoke about here, let me just create an example. Okay, so for our example, so example 1, let's say we are given f of x is equals to 2x cubed minus 5x squared minus 4x plus 3, right? And then now we are required to calculate this point here, the turning point. So calculate the stationary point. So we would first start by saying f prime x. So this means that we are converting to the parabola function, the derivative function. So once you see f prime, that means now we are converting to this one. So this is 6x squared, and then minus what? 10x, then minus 4, right? But then if we want the local minimum and the local maximum, your stationary points, note that f prime x is equals to 0 at stationary points. Because we say the gradient there is 0. So we want to have 6x squared minus 10x minus 4 is equals to 0. Now, if you can try to divide all these numbers by 2 here, because it's a common factor, all these numbers are divisible by 2. When I end up with 3x squared minus 5x, and then minus 2 is equals to 0, which this one, I believe we can factorize. So if we factorize it, it's going to be 3x and then plus 1, and then here it's supposed to be x minus 2, right? So this is going to give us x is equals to negative 1 over 4, x is equals to 2. Now, let's assume that this are our values, negative 1 and then 2. Remember, what I just did here is that I took the parabola function equated to 0. But then if I take the parabola function and equate it to 0, what is it that I'm trying to find? I'm trying to find the roots. I am trying to find the x-intercept, right? So these are my x-intercept. But this x-intercept, note, they correspond to the local minimum and the local to the local maximum and the local minimum. They correspond to local max and local mean. So now I've only found the x coordinates. In order to find the y coordinate, I have to take this x coordinates and then substitute them back into the original formula. Because remember, the y coordinates that I'm trying to find are on the y graph, are on the cubic function, not on the parabola function. They are on the cubic function. So that means that's f when x is equals to negative 1 over 3. So I'm going to have my negative 1 over 3 cube. So I'm substituting into that original formula. 1 over 3 square minus 4, negative 1 over 3, and then plus 3. Now, when you punch that into your calculator, you get your coordinates of the turning point, which here, this will give you what? So this is giving us a value of 100 over 27, meaning our coordinates are now what? Negative 1 over 3 is 200 over 27, right? Okay, and then now, what do we do in order to find the other coordinate, which obviously would have to be our local minimum? So we would have to say, again, if we substitute into the original formula, and then 2, so that's 2 to the exponent of 2 to the exponent of 3, and then minus 5, 2 to the exponent of 2, minus 4, 2, and then plus 3, right? Which is now giving us negative 9, right? So if it's giving us negative 9, we know that our next coordinates for this one, the local minimum, is now 2 is to negative 9, right? So now we have got to the first part of the cubic function and what it actually tells us, right? So it's going to help us to find the local and the local minimum and the local maximum point by taking the derivative and equating it to 0. Sharp. But then is it the only thing that we can get from that? Let's now check. Okay, so now that we've found those points, let's look at what other information we can we can actually find using that. So note that we had our turning points already. Here we had a -1/3 is 200 over 27. That was the local maximum. And then here we had 2 is to -9. That was the local minimum. Right. Cool. Now, suppose that we want to find where is our f of x increasing. But then we want to find that using our derivative graph. So we would soon find out that where f of x is increasing, it's actually where your f prime x is greater than 0, meaning where your f prime x is above the x-axis. So this is where your yellow graph is above the x-axis. Now I want you to take a look at this. Look at all the points where we see our yellow graph being above the x-axis. What is it that you spot with the cubic function? Now you can see that the cubic function at that particular time, it is doing what? Increasing, right? So again, take a look at this point here. We say that the parabola function is above the x-axis. The parabola function is above the x-axis. Check what is happening. Your cubic function is actually increasing. Your cubic function is actually increasing. Now you can say maybe that's a coincidence. Let's check here. Again, our f prime x is above the x-axis. Our parabola is above the x-axis. Just take a look at what is happening to the white graph. It is increasing, right? Can see that from this point all the way it's doing what? It's increasing, right? But then it's increasing at the very same point whereby we see your f prime x being above the x-axis. So in other words, we can conclude that where we see our f of x increasing, that's where our f prime x is above the x-axis, meaning between which points we can now use the stationary points to answer that. Now that we found the stationary points, we can say when x is less than -1/3 or when x is greater than 2, right? So it's in between which point? It's in between this point here. You can see here it is increasing in between this point. What is your white graph doing? It's increasing here. It's increasing. What is your white graph doing here? It's increasing as well. So starting from this point here, it's increasing. Now, what if we want to find where f of x is decreasing? So f of x is decreasing. We would note that f of x decreases exactly when your f prime x is now below the x-axis. So f prime x less than 0. So when your f prime x is below the x-axis. Now let's check between which points is your f prime x below the x-axis. Now if you mark here, you can see that this is where your f of x is below the x-axis. Now what is happening to your white graph? Now starting at this point, we can see from that local maximum point all the way to that local minimum point, what is your cubic function doing? It's decreasing. So we can actually spot that, oh, your f of x is always decreasing when we see your f prime x being below the x-axis. So that means in writing that one, we'll say when x is an element of starting from the local maximum point all the way to the local minimum point. So x element of -1/3 to +2. Or you can write it in this notation, which is x greater than -1/3, but x less than +2. So you see how that actually help us to identify what is going on. So it tells us about the behavior. This function here, f prime x, this parabola function, is telling us about the behavior of the cubic function. So, okay, now that we've explored that, we've explored how we can actually use the f prime x in order to get how our cubic function behaves. But then what about the green graph, the straight line graph, the second derivative? What does it actually tell us? Now, before we can get to what that one tells us, there is the last thing that I want you to note also about the f prime x. Now, you did note that I wrote a point here which is called the point of inflection, which is also another stationary point. But then that stationary point is actually obtained by finding the axis of symmetry. The axis of symmetry of f prime x is actually the point of inflection. The point of inflection. Now we know how to get the axis of symmetry in a parabola graph, right? So in a parabola graph, the way to get the axis of symmetry is, you know that you have to say x is equals to negative b over 2a. But if you don't have an equation, you can simply get the axis of symmetry by taking the x-intercept, add them together and divide them by 2, right? Because the axis of symmetry is actually the midpoint of your intercept. So we can find the axis of symmetry by saying negative 1 over 3 plus 2, and then that divided by what? By 2. So I'm taking the x-intercept here and this x-intercept divided by 2. But then you can see that this x-intercepts are actually the x-coordinates of the what? Of the local minimum point and the local maximum point. Those are the intercept of your stationary points, your two stationary points. So to get the third stationary point, you just take this stationary point plus this stationary point and then divide by 2, right? And then when you do that, you get the point of inflection. So this is going to end up giving us 5 over 6 positive. So 5 over 6, right? So that's where you'll have your point of inflection there. So that means, in other words, we do understand now that the axis of symmetry from the yellow graph here, from f prime x, is also telling us about the point of inflection, right? So those are the things that you can actually deduce from your f prime x, from your derivative function. But then if we want to know about the concavity, this is something else now. We want to know about the concavity, then this is where we consult our straight line. Now, what we do with the straight line is that we're going to draw it to be straight in line with the point of inflection, to be straight with the x-coordinate of the point of inflection. So we're not going to draw it to cross here, but then we're going to draw it to cross along the x-axis, but then straight in that line of the point of inflection, straight on that point of the of inflection, right? So, but then the line must intersect with the x-axis, right? So if we have our coordinate here, we just extrapolate and then place it here and then draw a straight line like that. So this is going to report to us about concavity. So the f double prime there is actually telling us about what? The concavity. So second derivative will report to us about concavity. But then the concavity is always in relation to the point of inflection. So there is no concavity without point of inflection. Because what is the point of inflection? This is where the graph changes concavity. So point of inflection is the point where the cubic graph changes concavity. So this is where the cubic graph changes concavity. So okay, let's look at that. Now, if they ask you where is your f of x, meaning the cubic function, concave up. Where is f of x concave up? Now we know concave up is this shape here. Once you have a shape like this, this is concave up. Now where do we see our graph being concave up? You can see that it's starting from this point. Remember, at the point of inflection, it's not concave up, it's not concave down. It's where it changes the concavity. So where do we start having a shape like this? We start having that shape right after this point of inflection. But I want you to look at the behavior of the straight line. Just after this point, what is happening to your straight line? Your straight line is above the x-axis. So in other words, we can say when your f double prime is greater than 0. So when your straight line is above the x-axis, that's where we have f of x being concave up. So concave up, it's up the x-axis. It's above the x-axis. So you have here, we will look at your linear being above x-axis. The straight line being above the x-axis. The straight line starts being above the x-axis right after this point here, right after the point of inflection. So this is supposed to be when x is greater than, remember we calculated it, and then we found that that value there, we said it was 5/6. So that's 5/6. So if we say our point of inflection here is 5/6, then that means it starts being concave up after the point of inflection, which is x greater than 5/6. Now again, where is the graph? Where is f of x concave down? Where is it concave down? Right. Now concave down means that where do we find the shape occurring? Right. Where does your f of x start having that shape? Now you will note, you go to the point of inflection and you note that just before the point of inflection, we have that shape concave down. So that shape happens before it reaches the point of inflection. And then how do you write that mathematically? We're going to say this is when our f double prime x is less than 0. Look at your straight line, what it's doing. It's concave. When your cubic function starts being concave down, what happens to your straight line function, your linear function? It's now below the x-axis. So it's now below x-axis. So at the point where your straight line is now below the x-axis, what is the shape that is formed by your cubic function? It is the concave down shape. So that happens when x is less than the point of inflection. So x less than 5/6, right? But then again, if you don't want to look at it based on the straight line, you can also look at it based again on the f prime x. This can also tell you about the behavior. So for all the points when your f prime x is decreasing, this is concave down, right? But then the moment it starts increasing, what happens? Now it becomes concave up, right? So now it becomes concave up. So these are the relationships that you need to observe when it comes to your cubic function, your parabola function, and your straight line function. So they open up a way of understanding what actually goes on in your cubic graph. So please find a way to incorporate that into your calculations, and then also when you are practicing your past exam papers, and see if this strategy is going to work for you. With all that being said, guys, thank you for watching the lesson. Thank you for watching up until this time. Please press the thumbs up button if you've enjoyed the lesson, and then you have also found it helpful. And if you've been watching the videos and haven't subscribed yet, please hit that subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.